Welcome to the second seminar of the Materials Characterization Online Seminar Series organized by Quantum Design. My name is Arianna Ramberti and I am the Marketing Manager at Quantum Design Italy. Today's seminar will start with a brief presentation of our company Quantum Design. Then we will hand over to Dr. Anthony Begivan, Senior Application Scientist at our partner company Dura Magneto-Optics. I'm now going to hand over to Simone Pazziani for the introduction.
So hello everyone, good afternoon. I'm Simone Pazziani, I work as Sales Manager in Quantum Design. Today we are going to talk about the magneto-optic applications, exploiting Kerr effect using our NanoMOKE 3 platforms, optical magnetometers and microscope. But before to start, I would like, for people who doesn't know us yet, to introduce Quantum Design, and I will do it with a really brief video. So we will be back in 90 seconds.
Quantum Design is specialized in the pan-European sales and service of sophisticated scientific instruments and components for research and development. We are part of the Quantum Design International Group based in San Diego, who has an international network of subsidiaries in all major technological centers worldwide. The comprehensive Quantum Design product range comprises tools for the measurements of mechanical, optical and thermal properties in materials sciences and solid-state physics. Temperatures close to absolute zero and high magnetic fields are possible. Other core technologies featured by Quantum Design include spectroscopy and imaging with special technologies like imaging spectroscopy and scientific cameras from X-ray to infrared. The Quantum Design Electron Microscopy Group offers a complete range of related products. The range of optical components like filters, polarizers, scientific light sources and light measurement systems provided by Quantum Design is unparalleled in Europe. Instruments for the characterization of biophysical phenomena round off the portfolio.
For more than 50 years, researchers all over Europe have benefited from our expertise. 120 employees provide a sound and independent advice in 20 European countries.
Okay, here we are back. Now it's time to hand over to Anthony for his presentation. Thank you very much, Anthony, and welcome.
Thank you, Simone. Thank you very much for the introduction. And thank you, Arianna, as well. And thank you for giving us the possibility to give this webinar. I would like to thank everyone in the audience who's attending this presentation. I hope you find it any useful. So my name is Anthony, and I'm Senior Application Scientist at Dura Magneto-Optics. In the talk today, I will talk you through one of our products, the NanoMOKE 3. The talk will be divided into two sections. In the first section, I will present the machine from a hardware point of view, so you can visualize what the machine looks like, and I will highlight the key performance of the system. In the second part, I will present some of the possible applications of the NanoMOKE by showing you a few papers that have relied on magnetic characterization using a NanoMOKE 3. So the NanoMOKE 3 is a combined magnetometer and microscope based on the magneto-optical Kerr effect. It's a magnetometer, so you can obtain hysteresis loops, and it's a microscope, so you can also acquire magnetic domain images. So first of all, I would like to briefly introduce what the Kerr effect is. It is an effect that occurs between a magnetic medium and polarized light. In the setup, we focus a laser beam with known incident polarization. We focus it onto the magnetic sample so that the focused laser beam is about 2 to 3 micrometer, which makes the measurements very highly localized since we are sensitive to the changes in magnetization under the laser spot. Upon reflection on the magnetic sample, the light undergoes a change in the polarization direction known as Kerr rotation. And sometimes the incident light, which is linearly polarized, becomes elliptical, which gives rise to what is called the Kerr ellipticity. So this is what the NanoMOKE 3 measures: Kerr ellipticity and Kerr rotation. There exist 3 different geometries of Kerr effect, known as polar Kerr. So polar Kerr is when the magnetization lies in the plane of incidence of the polarized light, but along the surface normal of the sample. There is the longitudinal Kerr effect, which is when the magnetization lies in the plane of incidence of the polarized light and in the plane of the sample. Finally, there is what we call the transverse Kerr effect, which is when the magnetization is in the plane of the sample, but perpendicular to the plane of incidence of the light. So the NanoMOKE 3 is sensitive to all 3 Kerr geometries. So this is what the system looks like. So you can visualize what it looks like and how much space it takes in a lab. There is an electronics rack on the left-hand side and an optical table on the right-hand side. The rack contains a PC, a controller unit, and a set of power supplies to control the electromagnets. In this gray box here on the table, this is where all the optics is contained and carefully aligned. The polarized light exits the box and reflects onto the sample, which is attached at the end of this sample stage. To apply some magnetic field, the user has the choice between 2 types of electromagnet. So there is, you can see a quadrupole magnet on the floor, and there is a dipole magnet at the back on the optical table. Depending on the geometry of the measurement, the user has to select the correct optics and the correct mount to get the right Kerr effect. It is very easy to switch from one geometry to another, and I've got a short video showing that. So this is me in the lab, going from the polar Kerr geometry to the longitudinal geometry. So you just need to take out the polar optics with 4 screws, remove the sample stick where the sample is attached, simply load your in-plane sample, and then select the right optics for the in-plane measurement. And you see, just tighten 4 screws and everything is aligned in the box, and that's all that needs to do. Of course, you need to refocus your laser after that, but it is very simple. Everything is carefully aligned. You can easily switch from one geometry to another. A few words about the quadrupole. So the quadrupole electromagnet allows the generation of fields along X and Y, or any direction in the XY plane. The nominal maximum field is 1,200 Hertz, or 1.2 kilogauss, with a sample space of roughly 30 millimeter by 30 millimeter. There is the possibility to go up to 2,600 Hertz by adding some pole extensions at the end of each pole of the quadrupole. The quadrupole magnet is compatible with longitudinal and transverse measurements, as well as polar measurements. For the generation of higher fields, we offer 2 dipole options: one small dipole that generates up to 6,000 Hertz of field, and a stronger dipole for fields up to 12,000 Hertz. So needless to say that because this is a dipole, only unidirectional fields can be applied. We also have the possibility to take measurements at cryo temperatures, and for that we have 2 cryo options. The first one is a microstat from Oxford Instruments that allows MOKE measurements between 4.2 Kelvin and 500 Kelvin. It cools down very quickly. It's a nice system, but I find it a little bit noisy there's a lot of vibration carried in the system. When transferring helium or nitrogen into the cryostat, it is very easy for the tubes to introduce some vibrational noise in the measurements. For vibration-free low temperature measurements, we work with Montana instruments. They offer a helium-free cryostat, but the helium is recycled, which means that there is no need for the user to provide their own liquid helium. The level of noise is really minimum, as evidenced by these two loops taken at 5.5 Kelvin. These are loops taken on a 20 micron wide microwire made of thermalloy. The loop on the left was averaged over a few cycles to reduce the signal to noise, to increase the signal to noise ratio, whereas the loop on the right was a single shot. So you can see that even the single shot loop looks very clean at 5.5 Kelvin. This next slide is to say that there are two ways magnetic domains can be acquired, either through scanning Kerr microscopy or through CMOS microscopy. The pros of each technique are listed here. The SKM offers the best sensitivity and a spot size of between 2 and 5 micrometer, but the CMOS offers higher acquisition speed, which is better for fast-moving domains. Also, the image quality is better on the CMOS since the image acquisition is in parallel and is not the result of rastering the surface with the laser spot. So this is an image obtained with the CMOS camera, and it is showing the US Air Force 1951 resolution test chart. I don't know if you're familiar with this sample, but this is basically a series of lines, horizontal and vertical, with decreasing width and spacing. And this is typically the sample we use in the lab to quantify the optical resolution of our SKM and CMOS imaging. So this concludes the brief overview of the NanoMOKE 3 hardware. Now, the main focus of this talk is to spend some time on the application side of the machine. As I explained at the beginning of the presentation, I will introduce some scientific papers for which the NanoMOKE 3 was used for the magnetic characterization. I will start with some very easy examples that you can easily understand, and I will end with some rather complex magnetic systems, but I will try, however, to keep the explanation as simple as possible. So what is the NanoMOKE 3 used for? So this is a list of research areas where the machine finds useful application. It includes MRAM or magnetic logic, MTJs, basic magnetic material R&D, or some more complex spintronic devices. In the first example, I'd like to show some relatively basic magnetic thin film study. This is what researchers all have to face at some point, and this is what I had to face during my PhD. This is the optimization of my samples. So here the aim was very simple. It was to characterize the magnetic properties of an ultra-thin film of cobalt iron boron, or COFEB, and to optimize this stack in order to get the desired magnetic properties. The study involved the presence or absence of tantalum buffer layer, and the thickness of the magnetic COFEB was investigated as well. So the first sample was a simple stack of platinum COFEB platinum grown directly onto silicon with DC magnetron sputtering without any tantalum buffer layer. Polar MOKE was used since at a thickness of 0.8 nanometer of COFEB. COFEB exhibits perpendicular magnetic anisotropy, so a very strong out of plane signal. This figure shows the domain structure after the sample is fully saturated with a strong 300 Ørsted field. And then the field is subsequently reduced and applied in the opposite direction. We can see that the magnetization reversal happens via the nucleation of a vast number of domains randomly distributed across the sample, and each domain grows as the magnitude of the applied field increases until they merge and the whole sample switches magnetization. Now, let's take a look at the domain structure if we introduce a buffer layer of tantalum. So this is the same stack as before, but grown this time onto 1 nanometer layer of tantalum. We see a completely different behavior with the nucleation and propagation of a single domain until the whole field of view switches magnetization. So it's quite amazing how a few monolayers of tantalum can drastically change the domain behavior. So to understand the reason behind these two different domain patterns, we did some atomic force microscopy to investigate the topography of the samples. So the top image shows the surface of an 8 nanometer layer of platinum grown directly onto silicon, whereas the bottom scan shows the same surface, but when the platinum is grown onto tantalum. So for this scan, it was 2 nanometers of tantalum. The result is quite striking. The platinum grown on silicon is very rough, whereas the growth of just 1 or 2 nanometer of tantalum as a buffer layer has the advantage of making subsequent layers really, really smooth. And so this explains the domain structures that we just observed. The sample with no buffer layer has a lot of nucleation sites in the structural defects where the anisotropy is weaker, and also a lot more pinning sites where the domain walls get trapped easily. Therefore, for the rest of my PhD, it is the sample with the tantalum buffer layer that was preferred for the rest of the study. After that, we decided to study the influence of the COFEB thickness on the hysteresis loop and the coercivity. So those loops were obtained for a COFEB thickness going from 0.4 nanometer up to 0.9 nanometers. And we can see that there was no real differences. The squareness of the loops was the same, which shows a well-defined out-of-plane easy axis. Also, there is no trend, no real variation in the coercivity, which indicates that the switching mechanism is the same for all samples. So this is a very common use of the NanoMOKE 3. I have a magnetic system I'd like to study, but different parameters to optimize, the presence or absence of a buffer layer, cobalt instead of COFEB, maybe different composition of cobalt iron boron within the COFEB. The sample can be annealed, not annealed, annealed at different temperatures. Basically, you can study the impact of your process on the magnetic properties and choose which process conditions suits your goal better.
We have a question.
Okay, sure.
From Nicholas.
So I'm wondering if you guys have improved, or have you worked instead of having like the best resolution in the Kerr signal in the reflectivity, have you guys explored all the different approach? Yes, basically, if you do if you scan the temperature, basically, if you do a reflectivity measurements as a function of temperature, have you guys improved that kind of measurement, or have you guys experienced with that?
It's not something I have done during my PhD for that particular study. No.
Oh, okay. Yes, that I was curious about that. Thank you.
Thank you.
Thank you.
So in this next example, we combine thin film application, nanostructures, and potential spintronic devices, and application in non-volatile memory device. So the magnetic system here is very similar to the last one. It's going to be a platinum COFEB platinum structure, but this time the beauty of it, it is the substrate which is different. So this is a study of magnetic materials deposited onto a flexible substrate. So now the substrate is no longer traditional silicon. It is a polyimide, a very flexible substrate. And so the aim was to see if the magnetism would survive this change of substrate and to try to characterize the magnetic properties when the flexible substrate was flat and when it was bent. So one of the challenges of bendable substrates, as opposed to traditional silicon, is the increased surface roughness, which, as we just saw in the previous example, can drastically affect the properties of the sample. So for some reason, I couldn't get my hand on the colored version of the paper. So all the images to come will be in black and white. So those images show atomic force microscopy scans of the surface of a silicon chip on the left-hand side and of Kapton tape on the right. It is obviously no surprise that the silicon is very flat, with a measured RMS roughness about 0.4 nanometers, whereas the polyimide substrate exhibits an RMS roughness about 7 times higher. Note the value of the RMS roughness of about 2.8 nanometers, which is gigantic compared to the sub-nanometric layers of magnetic materials that are required in those studies. So the loop on the left is a polar MOKE loop of a thin 0.6 nanometer layer of COFEB deposited onto the polyimide substrate. And although the loop is not so square and sharp as the loops we can get on silicon, I find it very amazing to see such clean loop. Yeah, and I'm truly amazed that you can grow such thin layers of magnetic material on bendable substrate and still keep some magnetic signal. The graph on the right-hand side summarizes the remanent magnetization MR over MS and the coercivity HC of such a film when bent over a range of different radii. So I don't have exactly the picture of the setup used in this experiment, but this is basically how the measurement was performed. The flexible substrate was rolled around a stick, giving the film some curvature RC. The MOKE loop was taken for different radii of curvature. So they use different size rods to roll the film around and take polar MOKE this way. And it is impressive to see that the thin film retains its full remanent magnetization and coercivity under bending. And these characteristics are robust down to a very, very small radius of bending. This means that you can take your flexible substrate, bend it like crazy, and it will retain its magnetic properties. The next step in this study was to compare the magnetic properties of the same layer stack grown onto silicon or grown onto polyimide substrates. The magnetic properties studied include anisotropy fields, coercivity, and domain structure. So this graph shows the hard axis saturation field HK as a function of the COFEB thickness for silicon and flat polyimide substrates. It shows that films fabricated on the flexible substrates generally display slightly lower anisotropy for the same COFEB thickness due to the poorer substrate conditions. Nonetheless, the anisotropy remains very strong, and the expected 1/T dependence of anisotropy with increasing COFEB thickness is observed in both substrates. So as far as the anisotropy field is concerned, flexible substrates are really promising candidates for future magnetoelectronics applications. Let's take a look now at the hysteresis loops measured on silicon, flat polyimide, and bent polyimide for 6 different thicknesses of COFEB. So you see 6 different sets of hysteresis loops. Each set corresponds to 1 COFEB thickness. It is evident that the magnetization reversal process between the 2 substrates is different. The COFEB single layer on the silicon substrate always displays square hysteresis loops with sharp magnetic switching, which is an indication that magnetic reversal occurs via nucleation and propagation of a small number of domains. On the contrary, we can see that the loops taken on the polyimide substrates, either bent or flat, show an increased coercivity and a more slanted aspect. This is attributed to an increased domain wall pinning due to the presence of a higher defect density in the form of peaks and pits, as we can see in the AFM images. So those observations made with the hysteresis loops are confirmed with the analysis of Kerr microscopy images. So here, this is the reversal on silicon. Again, a single domain is nucleated at the center of the image and expands circularly until the whole field of view is reversed. Note that the first domain is reversed at about 66 Ørsted, and the full frame is reversed at about 90 Ørsted. So it takes about 30 Ørsted in this case to reverse the full field of view. Here on the polyimide substrate, we observe a larger number of nucleation sites and a stronger domain wall pinning, evidenced by a switching process that starts at about 150 Ørsted and ends at about 300 Ørsted. So the next question this paper asked was, can we grow and measure a bilayer on the polyimide substrates? And you imagine that if I ask the question, the answer has got to be yes. So this is the stack they went on studying next. It is an antiferromagnetically coupled COFEB bilayer. Thickness of the ruthenium was chosen to lie at the first antiferromagnetic coupling peak, and the tantalum platinum buffer layer was optimized to maximize the RKKY coupling magnitude. So the two platinum layers on either side of the ruthenium, which are marked T nanometer for the thickness, they stabilize the perpendicular magnetic anisotropy and can be used to tune the antiferromagnetic coupling between the two COFEB layers. Okay, so this is the two COFEB layers being antiferromagnetically coupled. So the MOKE loops displayed here show result on silicon here, polyimide flat, and bent polyimide for two different thicknesses of platinum, 0.3 nanometer for the loops on the left-hand side and 0.5 nanometers for the loops on the right-hand side. So although the loops look slightly different, whether on silicon or on the polyimide substrate, it is truly remarkable that the magnetic behavior and the antiferromagnetic coupling is kept and measurable on the flexible substrate. One noticeable difference between the two platinum thicknesses is the slanted transition in the case of thin platinum thicknesses, which is an indication of the reduced perpendicular magnetic anisotropy due to the thin platinum layers that are less able to stabilize the magnetic anisotropy on the rougher polyimide substrate. So to get a strong antiferromagnetic coupling and to get a strong perpendicular magnetic anisotropy, it is better to have a slightly thicker platinum interlayer. This next graph shows the magnitude of the RKKY coupling field Hj as a function of the thickness of the platinum interlayers. And it is quite amazing that bending the film to a radius of curvature of about 350 micron results in no significant change in the RKKY coupling magnitude. This is extremely promising for device application on flexible, bendable substrates. Now, is this finished? The answer is no. This paper took one step further and asked the following question. Is it possible to pattern this bilayer into a nanostructure and still be able to measure a magnetic response? And once again, you guess that the answer is going to be yes. The wires shown here were obtained via electron beam lithography and subsequent argon ion milling. The wires were magnetically characterized using polar MOKE, and the wires we see on this SEM image are about 10 micrometer long and 200 nanometer wide. So if we were to shine the MOKE laser spot at one of the wires, it would look like that. So even if the nanowire occupies only a fraction of the total spot size, it's not a problem. We can still get the magnetic signal from the reversal of individual wires. The signal would be quite low because the nanowire is very small, and therefore the loops will be a little bit noisy. But nonetheless, it's not because the nanowire doesn't occupy the full area of the laser spot. We can still get a decent amount of magnetic signal. And this is exactly what we observe on those MOKE loops. The top loop shows reversal of the thin film grown on polyimide substrate. And the bottom two loops show reversal of individual nanowires of width 370 nanometers and 210 nanometers. I find these measurements quite spectacular, and it tells you about the sensitivity of the measurements, and it also tells you that bendable substrates are extremely promising for the fabrication of advanced spectrometer devices. It is truly remarkable. So I know I went on and on and on about this paper, and you can find the reference of each paper at the bottom of each slide. But I just find it really, really amazing. Now, I'd like to move on to another application of the MOKE, which is magnetic logic. In this study from 2017, the in-plane shape of perpendicularly magnetized small elements was carefully designed to create a lateral shift register. The aim was to find a way to control the nucleation of data bits and to propagate those bits unidirectionally along the chain of elements. So the SPM images here show what the elements look like. They are composed of a narrow wire of about 100 nanometer in width, widening up into a 2 micron by 2 micron square. It is very important that the elements are not in contact so that the dipole field between neighboring elements can be used as a bias field. So the first step in this study was the controlled injection of the data bit into the chain. To do so, they first studied the switching behavior of rectangular wires only. Wires not attached to anything, no square at the end, just a pure rectangular wire. We can see that the wire width is much below the MOKE spot size, so we can see wire width much below 2000 nanometers on those graphs. It's exactly the same as before. You can shine your laser spot at a very tiny structure and still get a good amount of Kerr signal from that tiny structure. So the top figure shows the switching field of nanowires of different width. And it shows that as the wires become narrower, there is a strong reduction in the coercivity. The bottom graph shows the standard deviation of the switching field taken over an average of around 10 wires. So the bottom graph shows a reduction of around a factor of 2 in the variability of the switching field for the narrower wires compared to the wider ones. This reduction in variability is very important for making long chains of objects and to reliably and controllably control the injection of a new data bit in the chain. And so quickly, the fact that the standard deviation goes down with the wire width is attributed to the nucleation of domains happening deterministically at the ends of the nanowire all the time, rather than at random defects somewhere within the wires when the wire is too big. So if a narrow wire is joined to a wider one, the narrower wire can act as a domain wall injector. So this explains the shape I showed you before, a narrow wire followed by a big 2 micron by 2 micron square. Here, if we just take a simple 2-element device and we focus the laser spot, the MOKE spot on the rightmost element, we see that the resulting MOKE loop is shifted by around 100 Ørsted. So you see that this loop is not symmetrical about 0. There's about 100 Ørsted of bias field. This is due to the dipolar field of the leftmost element, the square element, acting on the ends of the nanowire of the second element. So this bias in hysteresis loop allows the creation of a NOT gate. So if a symmetric oscillating field is applied, such that the magnitude falls between these two switching field values, neighboring elements would switch from parallel to anti-parallel, but not the other way around. So if we apply the right field sequence, we can always stabilize the anti-parallel configuration compared to the parallel configuration. So this simple observation on a 2-element device was applied to a longer 8-element chain when the first element is square and the following 7 elements have the widening nanowire structure. So the central figure shows a set of Kerr microscopy images of the chain which is made of 4 layers of COFEB. As you can see on the left-hand side, you can see the film, the layer composition on the left. Because of the processing of the images in order to enhance the contrast, the elements appear widely separated, but in reality, they are just a few nanometers apart, just like the SEM images I showed you earlier. The bottom image shows the field sequence that is applied and the different field values for which states 1 to 9 were recorded. So starting with a strong positive field, all the elements in the chain are magnetized in the same upward direction. After the initial positive saturation, a field of roughly H minus prop, here the field is then reduced to H minus prop of about 500 Ørsted. It's enough to switch neighboring pairs from parallel to anti-parallel, but not the other way around. So initially, after the strong positive pulse, all neighboring elements are in the parallel state. So which layers switch on this initial step depends on the exact details of the nucleation in each element. And we've got very little control about which element switch first when we apply the first H minus prop field. So in this particular example, 5 elements switch after the first propagation field. So these are elements 2, 3, number 5 also switches. If you compare row 1 and row 2, you can see that element 5 is a little dimmer. And we switch 7 and 8 as well. Then we go on and apply a strong 500 Ørsted field. And we see that the right-hand side element of each pair switches up. As we can see from row number 3 now, we can see that the elements directly to the right of the pair, each circle pair, switches magnetization. If we continue cycling the field up and down between H propagation plus and negative, one element switches magnetization, and the pair of elements with parallel magnetization is slowly displaced towards the right. So this is, in this ship register, the bits of information are contained in each pair of parallel layers, which can be successfully moved unidirectionally under an oscillating field. When the pair of layers reaches the end of the chain, it is expelled from the ship register, and the chain reaches its ground state with all neighboring elements anti-parallel. So I've got a short video showing the switching of the elements with the applied field. So the first video will go very quickly. And you can see the propagation up, down, up, down, up, down of the elements along the chain. And we end up at the end of the field sequence with the bits in the shift register in the ground state, which is up, down, up, down, up, down, up, down. On this second video, this is a slow-mo. So you can visualize every element switch one after the other. It probably doesn't help that my arrows are slightly out of sync, but you get the idea. You can see the pixels go bright or dark, and you can see the propagation of the data bits. So the same concept was extended to a 16-bit device. And the principle is exactly the same as before. The chain is first saturated in one direction, and the amplitude of the field reduced in order to generate the initial state of the chain. So here, for this 16-bit register, they started with a strong negative field, about 1,200 Oersted, and they oscillate between H plus prop and H minus prop. So on applying this very similar field sequence as before, we can move the data bits unidirectionally to the right. The only small difference here compared to the study before is that the first element in this chain is no longer a square, but it is an element just similar to the other elements, which actually makes it possible to re-inject a new bit, providing the right field value is applied. So you can see that the field is oscillating between H plus prop, H minus prop. And if we look at step number 5 here, they decide to apply a field H injection, which naturally happens between the propagation field and the saturation field. And so if we look at row 5, we can see that they inject a new element into the chain. So I've got a short video of this one, where we start with a strong negative field, and then the field sequence is applied between positive propagation, negative propagation, and once in a while they re-inject a bit in the chain, and it all moves unidirectionally to the right. So this is one of the cool stuff that you can measure with a NanoMOKE 3. This is what I call the funky nanomagnetic logic. I've got one more application for you today, which will look scary, but it's actually quite fun. I'll try to keep the hardcore physics aside and simplify the results as much as possible. So 7 years ago now, the nanomagnetism group in Cambridge invented and measured this concept of 3D spintronics. The idea is very similar to the nanomagnetic logic device I just presented. It is based on the close range interaction between layers which are antiferromagnetically coupled. But instead of taking place in the XY plane, in the plane of the silicon chip, here the bits of information are propagated in the vertical direction. So this very simple and efficient shift register concept opened up the possibility to create three-dimensional microchips for memory and logic applications with a potential boost in the data storage density of conventional MRAM device architecture. So if we consider a stack composed of 6 ferromagnetic layers coupled antiferromagnetically, there are 2 possible ground states, either up, down, up, down, up, down, or down, up, down, up, down, up, as you can see from that slide. If the magnetization direction of the top 3 layers is flipped, we introduce a magnetic frustration in the system where the 2 antiphase domains meet. This magnetic frustration is shown by the asterisks, the 2 red asterisks, and is called a soliton. So the idea is to use this soliton as a data bit and to move it up and down the stack using the appropriate field sequence. So the stack studied in this paper is rather complex. It is composed of 11 magnetic layers, M1 to M11. And the stack was very carefully engineered so that a ratchet scheme was a ratchet scheme for unidirectional soliton propagation was inherent to the layer stack. So all magnetic layers were ultra-thin layers of COFEB, so steel, cobalt, iron, boron with perpendicular magnetic anisotropy. And 3 different thicknesses of COFEB were needed to realize this stack. And the antiferromagnetic coupling was dictated by interlayers of platinum, ruthenium, platinum, with 3 different coupling strengths, J0, J1, and J2, depending on the composition of each platinum, ruthenium, platinum interlayers. So the hysteresis loop here was obtained using a vibrating sample magnetometer. And we can see that the experimental curve was compared to a simple Ising macrospin model, where the layers switch as a single domain, and the magnetization is always aligned along the z-axis. So first of all, we see a pretty good match between the experiment and the theory, except for 2 extra transitions in the model, indicated here by the exclamation mark that I just circled right now on the screen. But secondly, we can see that the VSM loop is super complex and manages to capture the full switching of the 11 layer stack. The complex soliton injection and propagation can be inferred from the VSM loop and the careful design of the stack. And we can visualize the position of the soliton, which is represented by a red asterisk, after each field cycle. The reason why I'm showing this example in this presentation is because in addition to quasi-static VSM measurements, the propagation of the soliton can be probed locally using a MOKE in polar geometry and using a pulse coil. So this is what these 2 figures are showing. The top graph shows the field sequence applied to the soliton stack. It is composed of 250 microsecond single sine wave field pulses spaced every 5 milliseconds. The bottom graph shows the MOKE response as a function of time. This is a rather unusual way of presenting data. Up to now, I have showed relatively simple Kerr signal versus applied field hysteresis loops or magnetic domain images, but it is possible to plot Kerr signal as a function of time and to watch the Kerr signal vary with an external source of excitation. And this is what was done here. So they start with an empty soliton stack here, which is marked as E in the red bubble. And they inject a soliton at time 0 milliseconds by applying a large field, which is this very first large field to introduce the soliton into the stack. The injection of the soliton is observed in the MOKE data by seeing the drop in the MOKE signal after the first large field pulse. So the MOKE level depends on the depth of the soliton in the stack. So the higher the soliton is in the stack, the stronger the signal is, and therefore the higher the magnitude of the MOKE signal. So on subsequent field pulses with lower amplitude, the soliton is propagated up the stack, as we can observe from the changing MOKE levels. I would say if you look at the MOKE data, don't focus your attention on these spikes in the MOKE signal during and directly after the field pulses. This is partly some induction effects of the large field gradients present. What matters the most here is the level of MOKE signal in between the field pulses. So if you follow this red line, you can see that after each field pulse, the magnitude of it increases. So it goes more and more towards the negative side of the cycle, but the amplitude of it grows. And when we apply a fourth field pulse, we see that now the signal goes from large back to 0, which is the state of empty soliton. So if we wanted to re-inject a soliton into the stack, you see that all subsequent field pulses, the MOKE signal remains at 0, which means that the layers are in this E configuration, up, down, up, down, up, down, up, down, and the total Kerr signal is absolutely 0. So if one wanted to re-inject a soliton in the stack, they would have to provide a strong pulse, as they did here at time 0 milliseconds. This is quite a phenomenal study with pretty impressive results, and the study was further extended in the same research group. This is a paper that came out a year or so after the big soliton paper, and the principle is exactly the same. You can see that the stack is very similar, if not identical, to the previous one. The difference is that in this study, they decided to pattern the whole soliton stack into micron-sized dots. So each dot in the STM image is about 3 micron in diameter. And it is a tall stack of those 11 magnetic layers and complex platinum, ruthenium, platinum interlayers. Each dot was separated by about 20 micron in order to prevent the interaction between the magnetic structures during the MOKE measurements. So the distance between the dots and the small laser spot size makes it possible to probe individual dots. So these are the MOKE loops obtained on a thin film and on a 3 micron dot. these two loops simply show how sensitive the NanoMOKE 3 is. It is true that ultra-thin layers of COFEB exhibit a huge signal, but being able to probe the switching of 11 individual layers, especially M1, which is way down the stack, it is quite remarkable. Each magnetic layer is a few angstrom thick. The measurement is very, very localized to only the 3 or 5 micron of the laser spot, which is, to me, this is really, really impressive. This is remarkable measurement. So if you're not convinced of the beauty of the technique, I just don't know what else to say. These two loops are single shot loops, so they're obtained after only one field cycle. There is no averaging done, which is even more impressive. And similarly to the previous paper, the full solitone propagation can be studied by applying a carefully designed pulse field sequence. And by looking at the evolution of the MOKE signal amplitude, we can track the position of the solitone from the injection region at the bottom up to the top layer until it is fully expelled. So this is a schematic that helps visualize where the solitone is, and it shows propagation from M4, M5, M6, and so on until M11, until the top layer, until the solitone is fully expelled from the stack. A similar graph, so the graph at the bottom, the MOKE data as a function of time, was taken for the thin film. There is a similar graph in the paper for the 3 micrometer dots, but it shows some extra switching that the film does not exhibit. So I invite you to read the paper, and the reference is at the bottom of the slide, if you want further experimental results. So I would like to thank you for staying awake until the end. I'd like to finish with this last slide summarizing the key strength of the machine. And this is a map showing where DMO is implanted around the world. So you can see a strong presence in Europe and China, and a developing presence in India, South America, and North America. There's a list of some of our strong customers. We have 2 products, the NanoMOKEs in red and the macrowriters in blue. The macrowriter is a series of maskless photolithography tools and has become a very popular product for the sample fabrication side of research. But with that, I would like to let you read this final slide, and I would like to thank you all for your attention.
Thank you very much. Thank you very much for the very interesting and challenging application. We have already collected a couple of questions for you. What can we do if we want to go above 350 Kelvin, for example, up to 470 Kelvin?
The first cryo option, which is the microstat from Oxford Instruments, it has heating elements that can go up 500 Kelvin. So with this option, you can go to cryo, to helium, liquid helium temperature up to 500 Kelvin.
A question from Jyoti. Dear Anthony, could you comment on signal-to-noise ratio in samples with roughness due to patterning or otherwise?
I mean, that's a very good question. Most of the loops I showed here were average over a few field cycles just to improve the quality. I mean, the worst loops I'm showing are probably those single shot loops at the end, the one grown on the bendable substrate. I think it depends mostly on the magnitude of your magnetic signal. So most of what was done here was COFEB, which has a huge magnetic signal. So this one, you can get high quality loops, even single shots. if you go to different magnetic systems, you will have indeed to average over a few cycles. But when you think about it, the measurement is taken at about, I mean, the user can choose the frequency of the applied field. So it only takes a few seconds to get a decent average.
Jody will let us know if it's okay for him or you have further questions. In the meantime, Cesar asked, is it possible to measure with different wavelengths?
By default, the system comes with a 660 nanometer laser, which is a red laser, but there is an entry port that the user can use to plug in their own laser. I have to say that the internal optics in the gray box is optimized to work between 400 and 700 nanometers. So I would strongly recommend a wavelength in that range. If a customer wants to use a very exotic wavelength, we would have to recustomize the optics inside to make it compatible with such wavelength. But anything between 400 and 700 is fine.
So let's go on with a question from Durga Madhab, and he's asking, do you have any example of combined AMR and Kerr microscopy measurements?
I have in my thesis, okay, let me stop showing and I will show again. I mean, it's been published a lot. I've done my PhD in collaboration with National Physics Laboratory just outside London, and we took a lot of AMR and MOKE loops, and I know that's what they did a lot. Let me show you some results. So this is just, I mean, this is not an approved paper. This is just a chapter of my thesis. But yes, it is possible to take MOKE and AMR simultaneously with the system. So this is what the device looked like. We had these L-shaped wires. We had some AMR contacts across the wire. The domain walls were driven with magnetic field. And we used the contacts to probe simultaneously MOKE and AMR. So as you can see from this figure, we can synchronize the AMR measurements to the applied field, and therefore you can get combined AMR and MOKE measurements.
Next one, Varimalla, do you get any y-axis in terms of rotation or arbitrary units?
She also added, I mean in terms of Kerr rotation.
I mean, you can, I don't know if I will answer properly, but you can apply fields in the y direction with the quadrupole, and you can measure the changes of Kerr rotation along that HY axis. I mean, most of the loops I show, they say arbitrary units on the y-axis of the graphs. Okay, I'm with you. Every time it says arbitrary unit, it basically means Kerr rotation. Yes, that's correct. It's just that in the magnetic community, Kerr rotation is not really understood well. So, you know, people don't really visualize what 1 millidegree of Kerr rotation is. So it's always simpler to just display arbitrary units. But in most of the loops I show, yeah, it was Kerr rotation.
Okay, we have Jonathan. He's saying, thank you very much for a very interesting talk. Could you briefly say how you relate the MOKE signal to the magnetization?
Okay, and that's a very good question. The MOKE signal doesn't tell you which direction your magnetization points, but the MOKE signal is sensitive to changes in the magnetization. So typically what we study is hysteresis loops. I mean, that is 90% of the result I showed today. And so we know the system, we know the direction of the magnetization, and we know that when we see a drop in the signal, it means that the magnetization has switched from one direction to another. But if you gave me some plain signal like this, it's not like a VSM loop. It doesn't really tell you much about the state of the sample.
It seems we have no more questions. So I thank again Anthony, all the attendees, Arianna, thank you very much